Welcome to the lecture. We are actually seeing the data link layer, and we have seen that error detection and correction are the prominent functionalities of data link layer. Basically, it is the error control. Now, as we have seen, there are two strategies to deal with these errors. The first is error correcting, and second is error detecting. Basically, these are the two things which are done with special codes. Now, in the case of error correcting codes, it involves or requires including some redundant information, but that should be enough to enable the receiver to deduce that which exact error has occurred in the code received. Let me repeat, error correcting codes will have some redundancy, and that is sufficient to enable the receiver that where exactly in the received code the error has occurred. The second types of code is error detecting codes, where that will only have sufficient redundancy to allow the receiver to deduce that some error has occurred, but that receiver may not be able to find out where exactly that error has occurred. To summarize, both type of codes will have some redundancy, but the redundancy in error correcting will be sufficient to let the error know error has let the receiver know error has occurred and where it has occurred, whereas in the case of detecting codes, that will be only sufficient to let the receiver know that the error has occurred, but that receiver will not be able to find out where that error has occurred. So actually we are seeing those error detection and correction codes in this data link layer, because that is a prominent functionality as we have just seen, where the reliability is an issue, maintenance of reliability. So basically these error correcting codes are also used in physical data link, network and transport layer as well. We'll see. Now those two codes, error correction and error detection, have been used here after a long research in mathematics. So mathematics has given some great uh, research, and based on that the codes have been used and being developed and being used here. So is the uh, contribution of mathematics here. So the error detection and correction codes will be seen. The first such code, error correcting code, is Hamming code. There are many such codes, but we'll only see here the Hamming code. So some prerequisite that we need to know. As we have just seen, there will be some redundancy with the code being sent. What is redundancy? For example, if 101 is the message to be sent, with those 101 bits, that means there are 3 bits, some additional bits, which is called as the redundancy, will be required to be sent to the receiver. So that with those redundant bits, the receiver may be either be able to detect, or based on the bits, number of bits, will be able to correct the possible errors. Now here, the frame which is being sent from the data link layer will consist of the M data bits. This is called as the message, and based on those M bits, there may be some redundant bits which are called as R. So M are the data bits and R are called as the redundant bits or check bits. So there are 3 types of codes. One is called as the block code, next is systematic code, and third is linear code. In the case of block code, the R check bits are computed solely as a function of M data bits with which they are related. Now, as we have seen here, so R bits will be simply be calculated based on the M bits. In the case of systematic code, the M data bits are sent directly along with the check bits. And in the case of linear code, the R check bits are computed as a linear function of M data bits. What do you mean by linear function? Basically, that may be one XOR operation, for example. So for every bit of the code, there'll be a bit, maybe, for example, linearly calculated. Bitwise it is calculated in the case of linear code. In the case of, for example, XOR code, you can say. So here n becomes the total length of the block. N will be M plus R, and that is called as the NM code. NM code it is called as, because n is the total length and where there are only M data bits. So it becomes a code word, n bit code word containing all n bits, where there will be M data bits and R check bits. Now, interesting thing is that of the total n bits, there will be only M data bits. So the ratio which is called as the code rate will be computed as M upon n. How many data bits are there in the overall n bits? So in a noisy channel, because that will be there is a possibility of many errors, there will be many check bits required, and that's why the amount of data bit will be lesser. So this comes to somewhat, let us say, for example, one half of the total n bits. Somewhat near about half only M bits will be there. Whereas if the channel quality is good, less number of errors are possible, and error detection can only be done, and that comes to a ratio or code rate of close to 1. So M bits will be close to n, that's why the ratio will come to nearly 1. For example, if this is the code which is transmitted and corresponding code which is received is like this, so you can have an XOR operation that gives how many bits actually have changed in the transit. You know that XOR operation will simply tell you which bits have toggled. So based on the inputs, the sent one and the received one, the XOR operation will give this one. Obviously, receiver will not be having the actual or correct code. This is just an elaboration of how the XOR operation can give the number of bits for our calculation. Receiver will be only having this much of data. So the 3 bits have changed in the whatever that is being sent, or that was sent, and whatever that was received. Very importantly, here we are going to define what is called as a Hamming distance. The definition of Hamming distance or Hamming distance is the number of bit positions in which two code words differ. That is called as Hamming distance. Now we will see with one example afterwards, and that Hamming distance is basically called as, means it shows that two codes are d distance apart. For example, if two codes are differing in 2 bits or 2 bit positions, so that will be 2 distance apart. Now in this particular 2 codes, this one and this one, the bits, 3 bits are different, and that's why these 2 code words are 3 distant code, 3 distance apart. So it will require d errors to convert one into the other. Here if you see, if you change, now for example, this was changed as 1, 0 was changed as 1, the next 0 was changed as 1, and the third bit 1 was changed to 0. So these 3 bits were in error. So if you convert, or if you change these 3 bits into the original, we will get the original code word. Means if it is this is changed to 0, this is changed to 0, and this is changed to 1, we will get the original. So in effect, if there are 3 bit positions different, if you now change these 3 bit positions, you will get the original code. That means if d is the distance, it will require d errors. Errors means we are changing the bits to convert one code word into another code word. Now, you know that with some m bits, 2 raised to m possible combinations are there. So with m bits, 2 raised to 2 raised to m possible data messages are legal. They are possible and legal. But it is not that all 2 raised to m data messages will be legal, because there is a specific way in which the check bits are computed. For example, if you go from, let us say, 0 0 0 to 7, that is 1 1 1, there will be many combinations. So 7 different combinations, I mean 0 to 7, it is 8 different combinations are there. So here we are going according to binary format, but the way in which the different bits or the check bits are computed, not all bits can be valid, or not all code words will be valid code words. And that's why we need to concentrate and see how the valid code words are calculated. Now mathematically, the number of valid code words can be calculated is 2 raised to m upon 2 raised to n. That is, here n is equal to m plus r, and that's why 1 upon 2 raised to r are the possible combination of legal code words. Here we need to know that r is the redundant bits, and n is equal to m plus r. That is, 2 raised to m upon 2 raised to n can be written as 2 raised to m upon 2 raised to m into 2 raised to r. This goes 1 upon 2 raised to r are the possible legal code words. The error detecting and error correcting codes of the block code depend on the Hamming distance. Now this is very important. To reliably detect d errors, one would need a distance d plus 1 code. What I mean, let me once again explain this with this example. Now there were 3 bits in error. To detect these 3 errors, we will require a code which will be distance 4, that is 3 plus 1. So if these this code is being sent, and some 3 bits were changed, what is the meaning of distance 4? One code word will be different in, or one code word will be differing in 4 bit positions from the second code word. So if only 3 bits are there which are different, we will see that, or we can assume that, that is the second code word that is received is not a valid code word, because the second valid code word will be having a distance of 4 bits, or there will be 4 different code bits will be different. Here only 3 bits are different. So we can conclude that whatever that is received is in error, and there is 1 bit which is in error. So distance 4 bit will be required to detect 3 bit errors. In the same way, distance to reliably detect d errors, we will require a distance d plus 1 code, and to correct d errors, we will require a distance 2d plus 1 code. For example, as we have just seen, to detect 3-bit errors, we will require a distance 4 code. And to detect single bit error, we would require a distance 2d plus 1. Here d is 1 because a single error. So that's why 2 into 1, that is 2, plus 1, that is 3. So in for correcting single errors, we will require distance 3 code. In short, we need to able to we will be able to find there was a single bit error and to correct it if we are having distance 3 error, the distance 3 code. Now we'll see this with one example. So there are 4 valid combinations of the code words given here, some valid combinations. So it's in all 10 bits, where all zeros is the first valid code word, first all zeros and next sorry, first 5 zeros and next 5 ones is the second valid, first 5 ones and the second 5 zeros is the third valid code word. Once again, all ones is the fourth valid code word. Here, as we can see, each individual the minimal distance between any two code words is 5. If you consider this and this, these are the 5 bits which are different from this and this between these two codes, and that's why the distance is 5. The minimum distance I am telling between these two code words, the distance is 10, you can say, but the minimum among all those is 5. So the minimal distance of this code is 5, and that's why based on 2d plus 1 and d plus 1, this particular code of distance 5 can correct double errors, because 2 into 2 plus 1 is 5, and detect quadruple means 4 errors, 4-bit errors, because 4 plus 1 is 5. So now imagine this is the code which is received at the receiver. Now the expectations was there could have been only single or double errors. Now the whatever the code is received like this, but this is none of the valid code word is matching this. That's why the receiver detects that there is one error, and it can accept single or double errors. So receiver must deduce that the original code which was transmitted should be this one, second one. Why? Because the 2 bits, if I change, double bit error is there that the receiver assumes, and those 2 bits are changed to 1, that becomes a valid code word. So if you simply change any 2 code bits here, that is not any other 2 bits here, that is not going to make a valid code word here, but only specific these 2 zeros are changed to 1, the second code word is accepted or received or assumed. Now in the second example, here the code originally was was to be sent as the first one, all zeros, but there were 3-bit errors in the transmission, and that's why at the receiver this was the code which was received. But now the receiver is only accepting only or assuming only single bit or double bit error, and that's why in the previous example, as like in the previous example, it will conclude that the code which was sent has to be the second possibility, and it will wrongly conclude this, whereas the actual code which was sent was all zeros, because there is no way for the receiver to change these 3 bits into 0. It can only go max up to 2-bit errors. So it's a wrong conclusion by the receiver. Now we need to only consider here that one cannot perform double errors and at the same time detect 4 errors. So it is not possible. Either we can correct 2 errors or we can detect 4 errors. Now, error correction, as we have seen previously, the receiver had to check whether the 2 bits changing are going to give some valid code word. So it had to actually calculate all the possible valid code words, whether the bits whenever they are changed is going to give me a correct code word. That means the correction requires evaluation of each individual candidate code word, which may be time consuming. And with a simple logic, this time can be minimized. And this is very important logic that we need to know. If n is equal to m plus r, we get m plus r plus 1 less than or equal to 2 raised to r. This equation is to be always remembered. There will be some examples as well. M plus r plus 1 less than or equal to 2 raised to r. So if you are having some, for example, 7 bits, how many redundant bits are required? That can be calculated. So based on the relation, we will put the value of r right from 0 here as well as on the right side. So 7 plus 0 plus 1, 8, and 2 raised to 0 is 1. That is not less than or equal to. You go on putting 2 raised to 1, it is 2. It is still less than 7. So 2 raised to 2, 4, it is still less than 7. 2 raised to 3, it is 8. So m7 plus, what is that, 3, 7 plus 3, 10 plus 1, 11, less than or equal to 8, it is not valid. And if you now consider r is equal to 4, what happens? M is 7, 7 plus 4, 11 plus 1, 12, and this is 2 raised to 4. 2 raised to 4 is 16. So 12 is less than 16, and that's how this relation is satisfied, and that's why r can be taken to be 4. And this is how, for a given amount of m bits, data bits, we can calculate how many minimum check bits are required. 4, in this way. So now m is 7, r is 4, so n will be 7 plus 4, 11. Okay. So now the code word was b1, b2, b3, some code word of 4 bits of b1, b2, b3, b4 is to be transmitted. We'll check how that can be implemented with the help of Hamming code. Now, obviously, the check bits will be put in the powers of 2. That is P1, because 2 raised to 0 is 1. 2 raised to 1 is 2. P2. 2 raised to 2 is 4. 2 raised to 3 is 8, and so on. That's why these are the bit positions where the check bits or the parity bits, we can say, will be positioned. And the rest of the bits, that is M3, M5, M6, M7, M9, etc., will be filled with M data bits. That 16 and 9 basically is there, because if you go on more than let us say 7 bits, 8 bits will require those many bits. In short, the powers of 2 will be having the check bits, and the rest of the bits will be used for storing the data bits. So we'll now have one example where m is equal to 7, and as we have just calculated, r will be 4. So here, now we consider a shorter example. Here the message will be having m data bits 4, and that will be transmitted as 7-bit code. N is 7. Obviously, there will be 3 error control bits. And how these 3 bits are to be put, we'll see with this example. So obviously, out of those total n bits, that is 1 to 7, we know that the powers of 2 will be the check bits. So powers of 2 means 2 raised to 0 1, that will be a check bit. The 2, that is power of 2, that's why it is a check bit. And 4 2 raised to 2, that's once again that will be a check bit. So these are 3 bits which are check bits, and the rest of the 4 bits are the data bits. In all, this is a 7-bit code word. Now for each individual check bit, how will be calculating the value of that? Because we know in short the value of D, the message to be sent. We don't know what is the check bits, and that's how we are going to calculate them individually. Here, very important thing is that we are going to calculate the even parity. Even parity means for all the bits considered in that particular position, the parity of bits has to be even. So even number of ones, we can say. So for the bit positions, now we will first understand how each individual bit or check bit is calculated. Now we need to know how each individual right from 0, sorry, 1 2 3 4 5 6 7. So 2 is 0 is 0 0 0, 1 is 0 0 1, 2 is let me draw it, 0 1 2 3 4 5 6 7. So this is all zeros, this is 1, this is 2, this is 3, this is 4. Try to get it because I am not able to draw it properly. This is 5, this is 6, and all ones are the 7. Now based on the position of 1 2 and 4, so how many what are the bits? For example, in the case of, let us say, the first data bit is 3. So what is 3? It is 0 1 1. So if you see, now consider 1, this is only 1. So in the case of parity bit 1, it will be considered in all the data bits where the 1 bit is set. For example, 1 will be, the parity bit 1 will be considered in all the data bit positions. For example, the data bits are 3 5 6 and 7. So what is 3? It is having 0 1 1. So it has got this particular 1 here. So 1 will be used in the calculation of parity for 3. For 4, this bit is not set, so 1 will not be used there. 5, this particular bit is set, that's why will be used in calculation of 5. 6, this is 0, that's why it is not set, not used. 7, it is set, and so on. So that's why the parity bit 1, to calculate the value of the parity bit 1, we will see the values of the data bit 3, 5 and 7, because they all have 3, 5 and 7 have got their first bit set. So now whatever that may be, 1 0 1 for example. So if it is 1 0 1, so there are 2 ones already set and 1 0 is there, and that's why this can be made as 0, because if you set is 1, it will make the parity of ones odd. We want the parity to be even, and like that. So in the case of check bit 2, what is 2? It is 0 1 0. So the second bit is set. So all the data bits bit positions where the second bit is set. So for example, this is 3. Now 6 and 7. So 3, 6 and 7 are the data bits which will be considered while calculating the parity bit 2. Similarly, 4 will be using the data bits only 5, 6 and 7, because 4, 1, 0, 0, this bit where the data bits where this bit is set only are 5, 6 and 7. So this is how the parity bits will be calculated. Now why particular those bits? We can if you see these particular circles, you will get to know which parity bits are to be, as actually we have seen the actual logic previously. If you remember that, that is even better. You don't need to remember this, but this can also be considered. So for 1 parity bit 1, the whatever that is shown in blue are the parity bits. Now whatever that is shown in red are the data bits. Here we are getting the data bits 3, 5, 7 and 6, and the check bits 1, 4 and 2. For each individual check bits, the corresponding data bits which are shown here 3, 5 and 7 will be used, and so on. If any of the data bits is changed, the parity bit which is in that circle will be affected. For example, if it is 3 is changed, the value of the third data bit is changed, it will affect 1 and 2 but not 4. If 7 data bit is changed, it will affect all the 3 parity bits, and so on. Now here we'll take one example. The overall code of 7 bits was like this: 11001110. It's a 7-bit code. Now in the previous logic, the first or the check bit at 1 will be calculated based on 3, 5 and 7. They are already 2 ones, that's why the parity will be 0 to maintain the even parity. And similarly for bit 2, there are the bits will be the positions at which the data bits will be calculated is 3, 6 and 7. They are all 3 ones, and that's why we need to make the parity even. That's why one is required, and that's why the check bit will be 1. Similarly, for the fourth check bit, the data bits will be 5, 6 and 7. Here they are already having even parity, that's why the fourth parity check bit will be 0. So here we get all the check bits, and now we can have the code like this, because we already have only these. We did not have the value for 1, 2 and 4. We only had the value for 3, 5, 6 and 7, and then we calculated the parity bits, and we have a 7-bit code for now. So as you already seen, based on that, if you put the values here in the circles, you can confirm which bits are changing, which parity bits. So as part of that example, once again, if you see 1100101, the message was to be transmitted as, and that was received as 1110110, where the bits are from 1 to 7. If you see the bit number 5, that was in error, that was changed. Now how this error can be detected and corrected, we will see. Now 1110110 was the message which is received, that we are taking here. Now for the receiver, only this message is there, so it will calculate the parity once again as in the previous procedure. So for 1, first the value is 0. It will calculate the corresponding bits, that is 1, 1 and 1. So they are having odd parity, and the parity bit says that it is 0. So that is not correct because the parity does not remain even. That's why this is incorrect. So here we are taking 1. For the parity bit 2, the value is 1 and rest of the data bits are 3 ones. That's why the total goes to even parity. That's why this is okay. And we are taking it 0. So 1 means there is one error and 0 means there is no error. So at bit position 4, this is 0 and the rest of the 3 bits are 3 ones. That's why once again this is one error. So the overall value of 101 basically gives which exact position the error has been. So 101 means 5. That means bit number 5 was in error. So that this is what we have seen. Now the value of the Hamming code can be summarized. The detection of 2-bit errors is can be attempted. Correction of single bit errors can be done. Cost of 3 bits added to a 4-bit message with the example that we have just seen. Now we know that additional bits are required to send one message, but this cost is not that high. If you consider, if the redundancy was not there, we would have required retransmitting all the data bits, and in that case as well, there was no way for the receiver to correct those errors, and that's how the addition of those redundant bits is justified. So thank you.